Hi everybody, come for the part 2 of my lecture series, The Devil in the Detail. In this video, uh, I'm going to talk about the connections, fatigue and all about. Uh, Last session, we looked the massive forces of wind and earthquake. So, if we look at the Davids, or we are going to explore how a single bolt, a 2 millimeter crack, or a quick sketch or a napkin can make or bring down thousands of tons of steel. So, in the world of structural engineering, we have a saying actually, the bridge is only as strong as its weak connection. Today we go under the microscope, like to find out where those weak links hide and why they are so often overlooked until it's too late. Come, let's dive on it. The load path concept actually. Uh, the path of the load is very important. Uh, Gravity is like relentless. It is always looking for a way to the ground, actually. As we know, gravity is towards the ground, and in a building, in a structure, how the gravity is falling, or like how the loads are distributed to the foundation. So most catastrophic failure don't happen because the main beams were too small, or but uh, it actually because the glue, the connection holding them together fails. So think of the load path like a chain. If every link is made of high strength steel, but one link is made of plastic, the strength of the steel doesn't matter actually. The load path will actually it can be broken. Most failures occur at the hand-off point, the connection where one member passes its burden to the next. So, can we go across a small case study on Regency Walkway? The Hyatt Regency in Kansas City, was hosting a tea dance where hundreds of people were on the suspended walkways overlooking the atrium, as you see in the picture. Suddenly, a loud crack echoed through the room, and the walkways collapsed onto the dance floor below. Here, at that time, 114 people died. How we can overlook in this concept is like this wasn't a failure of the steel beams or the concrete. It was a failure of a connection so simple it had been overlooked by the engineers or like contractors or like any inspecting persons. That time, if they did that one connection in a more accurate way, this sad incident won't happen. So it remains the defensive lesson in why small changes aren't even actually small. This is a perfect example for that. The fatal math, original versus actual. Let's look at the math that killed. The original design called for a single long road to go from the ceiling through the fourth floor walkway and down to the second floor walkway. But the contractor found a 40-foot road too difficult to thread. They proposed a minor change. Instead of one, use two shorter roads. In the original design, the fourth floor beam only had to support its own weight. In the modified design, the upper nut had to support the fourth floor plus the entire weight of the second floor hanging below. So they doubled the load on a single nut without doing the math. The steel box that steel box beam literally op, split like it's open under the pressure. So why do things break exactly where they do? It's usually due to stress concentration on that area. Imagine stress as a river flowing through a piece of metal. If the metal is smooth and uniform, the water flow calmly. Correct. But if you put a sharp notch, a hole, or a square corner in the metal, the water bunches up and creates a whirlpool of intense pressure for this small change. So actually it's not a small, for us we can think that it's actually not a small change, but to the building it's a very small change. Um, so this is why we use rounded corners in high stress areas. A sharp 90-degree angle is a magnet of for failure in this area. When we see a crack in a structure, it almost always starts at a stress riser, a tiny point where the geometric forces or the force the stress to skyrocket beyond the what the material could handle. So if you talk about the fatigue, the paperclip effect, fatigue actually. So if you take a paper clip and try to pull it apart, you can't. It's too strong. But if you bend it back and forth, it snaps easily. This is material fatigue. So structures that endure cyclic loading, like a bridge with cars driving over it or a plane taking off and landing, everything suffer from this. Every time the load is applied, microscopic bones in the metal break. These tiny cracks grow slowly, leaving benchmarks that forensic engineers look for after a collapse. A material can be perfectly safe for a static load, but fail under a much smaller load if the load is applied a million times. So here a case study of 1967, the Silver Bridge collapse. So it is actually happening in West Virginia, where the collapsed that bridge into the icy Ohio River, I think. This happens during the rush hour. So who's the culprit here? Actually, it's an I-bar, a massive steel. What is I-bar? Is a massive steel, a massive, we can able to say it as a massive steel link in the bridge string. It causes only a very tiny crack or about like just 2.5 mm deep. But it being growing, that crack is being growing due to corrosion and fatigue. Because of the way the bridge was built, there was no backup. When that one crack reached its critical size, the eye-bar snapped and the entire bridge fell in less than 20 seconds. So it was a non-redundant design, meaning it had no plan B only. Um, so we can able to tell it as like most important safety concept in modern engineering is redundancy. In a non-redundant structure, one failure leads to a total collapse. In redundant structure, we design multiple load paths. It is required actually. If the plan A is not working, there should be a plan B actually. Uh, the to conclude this, the structural integrity is a chain. The most brilliant architectural concept can be defeated by a single misplaced bolt or an uncalculated mathematical error change in a drawing. So thank you. We'll be looking forward to the next lecture series.